Hello everyone. In this video I wanted to explore a little bit what we can do with the radial part of the hydrogen atom wave function and what kind of questions we can ask and what kind of physics we can explore with it. So I wanted to start out with an example here. Let's look at, for example, the n equals 2, L equals 0 radial wave function for the hydrogen atom. So I'm just gonna look that up. What is it in the book? R20 is 1 over root 2 a naught cubed, 1 minus r over 2 a naught times an exponential, where a naught is just some constant that is just a convenient way of writing a combination of other constants, but it's a nice, it's in distant units, and it's really the Bohr radius. So what does this function look like, and what can we do with it? So one of the questions we usually want to ask is, we've got this wave function for the particle. Where is it? Where are we likely to find it? What does the probability look like? And so if you remember, probability basically looks like the wave function squared. But here we've got only the radial part of the wave function. So we have to be a little bit careful when we talk about probability, because, for example, we're looking at, here we're basically just looking at the radial part. We're looking at really all angles if we're not looking at the angular part at all. And so let me draw a picture to kind of illustrate that, which is that if I have, it's much easier to draw in 2D, but if I'm looking at a small radius and I say, what happens, how likely am I to find a particle between, in this narrow range of radii, versus if I ask, well, let me use the same range of radii, but at the same sort of delta r, but at a larger r. So let me draw, not a great circle, but this is supposed to be the same delta r. I can't draw real consistent lines. But the point is, even though my delta r is the same, or is supposed to be the same, the fact that one of these is at a larger radius means that it's going to cover a lot more area. There's a lot more, even if the probability density is the same, is uniform throughout this whole 2D picture, just the fact that I've got a much larger ring here means I would be more likely to find the particle there. And so I need to basically account for that when we do any kind of probability calculation. Because the function itself doesn't have that in it. The function itself just gives the value of the probability density at a particular radius there. And so what that means in terms of math is that if we want to look at the probability as a function of radius, something like that, then what we really want to look at is the 3D version of sort of the area here. So this is like the 2D version. So what we would do is we would say, well, if we want to look at the total area in this ring, we would look at sort of the circumference times delta r. The 3D version is we look at the area of a sphere, which is 4 pi I squared, times the thickness of the sphere. So that's what we need to do in 3D. We need to look at this. We need to look at 4 pi r squared times the radial part of the wave function squared. So to really get an idea of what is the probability. So that's what we want to look at. So let me just erase the picture, and let's just, for this particular wave function, let's look at what that is. For n equals 2, L equals 0, P of r, then dr is basically this squared times 4 pi r squared. So I'm going to have, let me bring out the constants all out front just to keep them out there. Root 2 over a naught cubed. I have an r squared, 1 minus r over a naught, that's squared because I'm squaring the wave function, and then the exponential is squared as well because I'm squaring the wave function. That's just going to get rid of the factor of 2 there. So that is really the probability density that I would want to look at to make sense of what is going on with the electron in this particular state. So I'm going to switch over and I'm going to make a plot here. Actually, I'm not going to use Wolfram alpha. I'm just going to use something I already set up. So here I've written just in, I'm using Python to do this, but that's not important. Here's my wave function. here I am just setting, I'm basically ignoring some of the constants, and I'm setting basically a naught equal to 1. So I'm basically saying whenever I make a plot, any distance in this plot, like in the horizontal axis, is going to be in units of a naught, is essentially. So if it says 1 on the plot, that's really 1 a naught. 2, and if it says 2, it's 2 a naught. So that's my radial wave function, and then if I want to plot it, I can plot, this, and it shows me a picture. Let me zoom that in. So that's what it looks like. You'll notice it does some interesting stuff. It's got 2 peaks. And in fact, it actually goes to, it's actually going to 0 in between them. In fact, if you look at the original wave function before I squared it, you notice that, let me flip back here. So I drew a little picture there. Before I squared the wave function, if I look at this, for r equals 0, or for small r, or basically as long as r is less than 2 a naught, then this term is positive. And the exponential is positive, and the constant's positive, so it's positive. If r is greater than 2 a naught, then this term is bigger, and this whole thing is negative. So the wave function itself is positive, goes from positive to negative, which means it goes through 0 right here at 2 a naught. So that's what we're seeing. Then when we square it, the 0 is still 0, but the negative part becomes positive, and then we see that kind of behavior. So that's interesting. That means an electron in this state, you have some probability of finding it within this sort of small radius region, and some probability of finding it within this larger radius region, but actually you have exactly 0 probability of finding it at exactly 2 a naught. At that particular radius, you're never going to find that electron. It sort of lives in 2 regions. And that turns out to be important for the structure of the atom. Another thing that I wanted to mention is we can ask some different questions about probability. So as before, we can do expectation values, or we can ask actually a slightly different question. We already did one question, which was where was this 0? We actually just looked at the wave function and figured out where it was 0. That was really straightforward. Another almost as straightforward thing is we can look at this probability function, and we can say where are the peaks? We can see that it's got 2 peaks, but where are they? What are the actual radius values for them? That's actually not too difficult to find. We have to do a little calculus, but we can take this function, and how do you find the peak of a function? Well, one way of doing it is you take the derivative and you look at where it's 0. So we can do that here. We can take the derivative of this and say, where is it 0? And that's just complicated enough that I don't really want to do it myself, but I can go back to Wolfram Alpha. Now I can bring up Wolfram Alpha, and I can say, you know what? If I want to look at sort of where is this function, where's the derivative of this function equals 0, I don't care about the constant out front. So that's one nice thing. I can just, I'm not going to bother asking about that. So I can just say, where is the derivative of equal to this? So what I'm going to type into Wolfram Alpha, I'm going to use sort of the Mathematica. I happen to know Mathematica a little bit, so I'm going to use that notation, but sometimes Wolfram Alpha is not even picky about if you get the details right, so that's kind of nice. But I'm just going to say solve. I'm going to say take the derivative of, and what was my function? I'm going to say r squared times 1 minus, I'm going to set a naught equal to 1. Okay, so I don't have to worry about that. R squared times 1 minus r squared times e to the minus r. I'm going to take the derivative of that with respect to r, and I'm going to set that equal to 0. And I'm going to ask Mathematica to solve it. So let's see what happens if it actually does it. Awesomely enough, it did. It gave me 4 values. 4. But let's see, r squared, 1 minus r squared e to the minus r. That looks good. Oh, I know what it did. So what did it give me, my four values? Well, it gave me 0. Okay, yeah, so it's flat here, but that's a minimum. I don't care about that. It also gave me 1. And let's see. Did I mess up? Oh, I messed up writing something down here. I made one mistake in writing my equation here. I squared this. I forgot the 2 stays there. I have a 2 there. So I missed that. I noticed my solution wasn't giving me this one. So that's what I missed. I think my plot actually had it correct. I think I had it written correctly in my function. Yeah, I had an over 2 there. I just, when I entered it into Wolfram alpha, I didn't have that over 2. So I needed to say, change that to over 2. That's why this looked weird. But hey, okay, good, quick fix. So we find, yeah, 0 is the one we don't care about. R equals 2, that's the minimum where it's 0. But we also find this is sort of 3 minus root 5 and 3 plus root 5. Those are the other 2. Those are the peaks. What is 3 minus root 5? Can I get a numeric approximation to that? I can probably actually just do that in Python quicker. What is 3 minus square root 5? About 0.76. So I get a peak at about 0.76 a naught. And then 3 plus square root 5 is about 5.24. So let me flip back here. I've just drawn that on my graph. So what I found out then is I found out where these peaks are. There's a peak at actually a little bit less than a naught. And there's another peak at about 5, a little more than 5 times that Bohr radius. So that's one type of question we can answer, which is that peak is the most likely radius. It's sort of, if you remember your statistics, it's what they would call the mode of the distribution. So in this case, it would be that 5.24, because this is a peak as well, but it's not the highest peak. We know that just from looking at the plot. The other question we could ask is, if that's the mode, we could also ask what's the mean? What's just the average radius here? And that's where the expectation value comes in. We can look at, because what that really is that's what this is, the expectation value of R. But again, we have to look at, we want to make sure we include this 4 pi r squared in our calculation, because to account for the fact that at larger radii, there's actually more stuff out there. Otherwise, we're not really doing the integral properly. But otherwise, it's the same sort of thing. This is going to be this expectation value of R. I don't know if I can squeeze it on here, but let's see if I can. We're going to integrate the wave function times its complex conjugate, but here there's no complex numbers in here, so it's just real valued, so we're basically squaring it, and then with a 4 pi r squared. So we're going to have 4 pi r squared 1 over 2 a naught cubed, 1 minus r over 2 a naught squared, e to the minus r over a naught. Got rid of the 2 because I squared it. And then I have integrate that over r from 0 to infinity. And I'm going to check. I got to be a little careful about normalization, because that is going to affect what I get for my average value of R. The one thing that I'm curious about is that that I'm hesitant about is that, so here I've basically treating this as I've already done the angular integrals, and this is where that, remember I said that for the spherical harmonic functions, people have different conventions of defining them, and in some conventions they integrate to 1, and in some conventions they integrate to 1 over root 4 pi, and it cancels this 4 pi here, so I'm a little bit I want to be a little bit careful about that and just check which we're dealing with here. But how can we check that? What we can do is we can check this without the I'm sorry, I forgot the extra factor of r because I'm taking the expectation value of r. What I wrote down right here is just the expectation value of 1, basically. So if I do that, I should get 1. I should get 1 out. I should have normalized the wave function. That's actually how I can check this. So what I'm going to do is I'm going to come over here to Mathematica again, or Wolfram Alpha. And I'm just going to see, what is this integral that I've written out here? Is it 1, or am I going to get 4 pi? And that'll tell me which normalization I'm dealing with. So I can say integrate 4 pi r squared. Again, I'm going to use this normal. I'm going to set a naught equal to 1. That shouldn't affect anything because that's just a distance scale. So I have a half. I have 1 minus r over 2 squared. Whoops. And I have e to the minus r. And then I'm going to integrate that from r over r from 0 to infinity. So I'm just typing this integral into Wolfram Alpha, and it gives me, guess what? It gives me 4 pi. So that means we're just using the convention where the spherical harmonics have a 1 over 4 pi sort of built into them. What that means is if I want to find the expectation value of r and have it come out right, whoops, I'm trying to flip back. Here we go. Then I need to take out this 4 pi, and then I multiply by r because that's what I'm finding the expectation value of. So now that I've already typed this big integral in here, I can do that easily enough. I can put an extra factor of r in here, and I can do this integral, and I get 6. Comes out to a nice number. The average value, and so remember, I set a naught equal to 1, so this really means that the average value of r is 6 a naught. So that's actually interesting. That's another interesting thing to know. So here I've got my peaks of the distribution, my average, because this tail actually goes on for so long, this tail is exponential. It really goes off to infinity. The average value of radius is actually 6 a naught. It's actually outside, is actually even to the right of that second peak. Just kind of a little bit unexpected, but it's because I've sort of drawn it. I kind of haven't drawn how really far out this tail goes. Did I keep the plot? Yeah, there it is. Yeah, because even here you can't really see. I mean, that tail, that exponential keeps going, and that basically means the average is actually right out here. So those are interesting things to know about the electron. And what's especially interesting is to compare that. I make this smaller again, is we can compare that to the n equals 2, L equals 1 wave function. So remember this wave function, this was basically what, especially in chemistry, you would call the 2s orbital. But let's compare it to the 2p, the L equals 1. I've already got that function in here. I already programmed that up in Python, so if I just plot it, it shows it to me. You notice this one's actually, now it's in the orange. The interesting thing there is that it doesn't have this double peak structure, so that it's much less likely, you're much less likely to find the electron really close to the origin. I mean, the function's almost 0 for especially less than 1 here. It doesn't have this bump at low r, sorry. But it actually peaks at a slightly smaller radius. And the average, we would have to do the integral to figure it out. But that would be an interesting thing to do. But this has this kind of stuff has important consequences for chemistry, because this means that electrons in a 2p orbital if you have a multi-electron atom with electrons in both of these orbitals, that means the 2s. There's some probability, or another way of thinking about it is some fraction of the time, the 2s electron is actually inside the 2p electron. So that's going to partly shield the charge of the nucleus, because if this electron in the 2p state has it sees the nuclear charge, but it also has some fraction of this 2s electron's charge. That means the effective charge of the nucleus is going to appear to be slightly less for that 2p electron, and that's actually a noticeable thing that you can actually measure in atomic physics. And you can also compare, like, well, on average, where does this spend its time? Is the average radius larger or smaller? And I'll leave that as an exercise, or maybe a exam problem. But but those are the kinds of things you can do with a probability wave function. You can look at sort of peaks. Where is it zero? Where is the average? And the main thing to remember is just keeping track of these normalizations. And like I said, I ran into it here. There's just different conventions, and sometimes you just have to kind of crank a number or two to figure out which convention you're using, just to make sure you get the right answer out. And you've got this fact, the issue of these r squared and 4 pi is just important to keep track of what you need to use there. All right, so thanks for watching. I'll talk to you next time.